This video demonstrates the use of the break statement in a loop. We have a program that determines whether a given number is prime. Let's go ahead and run that program. First compile and then execute. So let's try 50. And 50 is not prime. We could try again and do something like 13. Is the number 13 prime? Well, it is, but does the program? Yes, program calculates correctly that 13 is prime. Cool. All right. So how does this work? Well, a prime number is greater than 1 and has only two positive divisors, 1 and itself. If there are more than two divisors, then the number is prime. And we have here potential divisors. We go through all potential divisors from 1 to a billion. And we check to see whether the potential divisor is a real divisor. If it is, then we increment a counter. So that counter is keeping track of how many divisors this number has. And if we get over 2, then we know it's not a prime number. And so we have down here, if the counter has exceeded 2, then we know it's not prime. And then we generate the output based on whether it's prime or not. If it is prime, then we say it is. If it isn't prime, then the program outputs is not prime. Okay, so if we were to do something like 4, we know 4 is not a prime number. 4 is divided by 4, 2, and 1. Those are the divisors of 4. And so 4 is not prime. That's correct. But it does take an awfully long time to calculate something so straightforward. The possible divisors of 4 are determined within the first 4 loops. Within the first 4 loops, the number 4 is known not to be prime, because in the first loop, the potential divisor is 1, in which case we're going to increment our counter. So we know already that there is one example of a divisor, and then pdiv increments becomes 2. 2 is a divisor of 4, and so we increment the number of divisors once again. Then pdiv becomes 3. 3 is not a divisor of 4, so we don't increment the counter. And then pdiv becomes 4, and we increment the counter, and it becomes 3. And from right there, we know that 4 is not a prime number in the first 4 loops. But the for loops continue all the way to 1 billion. And so we have 999,999,996 too many loops occurring. And that's why the program seems to take so long to calculate that 4 is prime. So here's how we can use a break statement to not calculate the other 1 billion minus 4 loops. What we're going to do is cut and paste the code that determines whether counter has exceeded 2. That's saying that the number is not prime. And then we're going to just break out of the for loop if the counter has exceeded 2, because if the counter has exceeded 2, then we know it's not prime, and so we don't need to keep checking for more divisors. So let's compile and run that program. So if there's a number 4, oh, look at that, that's almost instant. 50 is not prime. What if we still put a big number in there? It's not prime. It determines that this number, which I just kind of smashed the keyboard a little bit to get, is not prime. It determines that very quickly, probably because it's even, right? So it would have gotten at 2, it would have noticed that it's got that divisor as well. So this was very quickly determined. Now what if we did an actual prime number, like 13? Now it's taking a while. And that's because it's actually having to go through all 1 billion loops to determine that 13 is prime. Excellent, thank you.